This month's SBE Webxtra is brought to you by Wheatstone, maker of the intelligent IP audio network used by studios around the globe. The AES-67 compatible WheatNet IP intelligent network is the most comprehensive end-to-end studio network system in the world, with a full line of consoles, software apps, IP audio appliances, and third-party add-ons for any studio workflow, size, or purpose. Wheatstone. Well, good afternoon. I'm Chris Scherer, Member Communications Director of the Society of Broadcast Engineers and the co-host of this month's episode of the SBE Webxtra, the SBE chapter of the web. This is a monthly SBE meeting usually held on the third Monday of the month. The SBE is the Association for Broadcast and Multimedia Technology Professionals with about 5,000 members, mostly in the U.S., but also around the world. The host of today's SBE Webxtra is SBE board member Kirk Harnack, who is also the chair of the SBE Social Networking Committee. Hello, Kirk.
Hey, Chris. Glad to be here. Thanks for the nice introduction. How are you?
I'm just fine. How are you?
I'm glad we could all make it to the meeting, and all of you who are watching online, glad you're here as well. We have got a show today, an episode, a meeting today that I'm really excited about because we're going to get to cover some topics that are a little mysterious to me, and I'm sure a lot of other engineers. Jeremy Ruck is our guest. I've known Jeremy for some years, met him at the top of the then Sears, now Willis Tower in Chicago. And I forget if my protocol's right here, but let's welcome Jeremy Ruck to our meeting. Hi, Jeremy.
Hey, Kirk. How are we doing today? Good to be aboard and good to be with everybody today.
I'm good. And, when you and I met, we were part of a project that had to do with RF exposure to humans on the top of the Sears Tower. And since that time, in the intervening years since, you have your own consulting company, and you are doing a lot of television work, among other RF work. And I believe that's what we'll be talking about, television repack and some of the technicalities that go into the critical nature of getting an antenna, feed line, and transmitter to all talk to each other. Is that right?
Sure. Yeah, we've got some good data. Hopefully we can take a look at some of the things we look at when we're commissioning antenna systems, and then kind of whatever you want to talk about, and sort of the views that we've got from this side and how things are going on this end.
I'll be, as the show goes on, after we have our initial announcements, I'll be walking Jeremy through explaining some things about the repack, how that's going, some of the issues that come up during that. And then we'll get to talk about some of the real deep technical stuff about what Jeremy or any consulting engineer on site is going to be doing with a new antenna, a retuned antenna, and making sure it all works with the transmitter. But first, Chris Scherer is here with the beginning of the meeting announcements, things that are of interest to us as SBE members. Chris?
And here's your SBE member update for November 18, 2019. The SBE held its national meeting last month in Madison, Wisconsin. Wayne Pacina was sworn in as the new president of the SBE, as were the other officers and 6 directors. The SBE National Meeting was held in conjunction with the Broadcasters Clinic, a presentation of the Wisconsin Broadcasters Association, and the SBE chapters of Wisconsin. Part of the national meeting events was the annual membership meeting, and you can watch the replay of the meeting live stream on the SBE YouTube channel. Go to sbe.org/YouTube and you can find it, but don't do it now because you're watching today's Webxtra. So do it later. The 2020 SBE National Meeting will be held in Syracuse, New York, in conjunction with the Central New York SBE Chapter 22 Broadcast and Technology Expo. The SBE Awards, the Robert W. Flanders SBE Engineer of the Year Award in the fall. Bill Hubbard is the latest honoree. But did you know that all chapter engineers of the year are automatic candidates for the national consideration? So you should bring it up at your next local chapter meeting. More information on our awards program and the Chapter Engineer of the Year Award is at sbe.org/awards. On the webinar side, there is an upcoming webinars by SBE on the calendar. That'll be Thursday, December 12th. It's Workbench Tips. The author of Radio World's popular column and TELUS Alliance Western Regional Radio Sales Manager, John Bissett, will bring a combination of tips from his column and discuss the conversion to AOIP and what AES-67 means to you. This will be a free webinar and an easy way to earn SBE recertification points thanks to the Telos Alliance for sponsoring the webinar. For information on webinars by SBE, go to sbe.org/webinars. On the certification side, if you'd like to take an SBE certification exam, here are some dates to know. Local exams will be held at chapters the week of February 7, 2020. The application deadline is December 31, 2019. SBE certification exams will be held on April 21, 2020 at the NAB show in Las Vegas. The application deadline for that is March 9, 2020. And if a local chapter exam is just not convenient for you, private proctoring is available. Contact the SBE National Office for details. For more information on SBE certification, go online, sbe.org/certification. And that's your SBE member update for November 18, 2019. Kirk?
Chris, speaking of certification, I have gotten a letter and a couple reminder letters about my need to fill out some forms for recertification. Am I the only one who procrastinates about that?
No, as a former member of the certification committee and actually chair of the committee as well, you're not alone. It's common, and that's one reason the letters are sent. Certifications are valid for 5 years, and about the midway point, you'll get a reminder just saying, "Hey, so you're about halfway through, and if you want to recertify by points." Which you can do on, for most certification levels, there is a point system that you can just recertify by submitting a form with some points and a little record keeping. It's just a reminder to keep track of that kind of thing. So it's not a last minute, oh boy, 5 years has gone by and I haven't written anything down. We actually have an Excel file on the SBE website under the certification heading. It's pretty basic, but it's a quick and dirty way just to enter some information, put in the points. It'll tally them for you. They're already broken down into the categories. Just another tool, pretty simple, but very easy to use. And actually, I keep that form myself. So when I need to recertify, it's a lot quicker and simpler for me to go back and tally things. But as far as your letters, I said you'll get one at about the halfway point at 2.5 years. You'll also get them closer to the actual expiration date as well. So we want to make sure we give you every chance to do what you need to do to become recertified and keep your certification active. So don't put it off. Keep track of your points and certainly renew when your certification comes time to be renewed.
I just need to keep reminding myself that filling this form out for recertification is a lot like mowing the grass. And that is when you get the lawnmower out and you got the gas out and, it's got oil in it and you're about to pull the ripcord. That's half the battle right there. The lawn at that point is half mowed. So it's getting this out and getting the pen out and looking at your calendar. And maybe you've kept track of things that you've done. And some things I have kept track of. So I just want to let other SBE members know that you're not alone probably in doing this at the last minute or after several promptings. So I got to do that too.
Yep.
Thanks a lot, Chris.
And by the way,
updates.
Just by watching today's SBE Webxtra, you've earned half a point. It's like attending a local chapter meeting. So be sure to write that down as well.
What do the host and the moderator get? What, half a point?
A laurel and hearty handshake.
I wonder what our guest gets. Our guest is Jeremy Ruck. I want to welcome Jeremy back in. Hi, Jeremy. Glad you're here.
Hey, Kirk. Thanks a lot. Good to be back with you.
So you've been involved so much with TV and radio, and at the real points where the rubber meets the road, and making sure that the RF signal gets out to people in an acceptable or maybe even darn near perfect format. And I understand you've been pretty busy with all this television repack. I wonder, some of us guys in the radio biz, we're not up on entirely what the repack is all about. I got to sit at a dinner table with some folks from T-Mobile about a year ago at an SBE dinner. So I got, some information there. I try to keep up with the news, but for those of us who don't keep up with the news, what's the elevator speech on what this TV repack is all about?
Well, the thing, just to begin with, is that everybody's been talking about this being the repack, and the reality of it is we're actually in our third repack now. The first repack happened with the advent of the cell phones, and that's when we lopped off channel 70 to 83. And that was given to the old Spe systems and those guys, the original cell phones. Then when we did the DTV conversion 10 years ago, then we lopped off everything from 52 to 69. So now, up until this repack started, we were basically looking at channels 2 through 51. And once we're all completed with this, the remaining spectrum is going to be 2 through 36. And of course, this is a reminder to everybody, there's no channel 37 stations out there because that's a frequency or channel band devoted to radio astronomy. And basically what's taking place here is as cell phones, wireless phones have become more prevalent and everybody's got them, more and more are available. What we find is you need to have more and more spectrum to accommodate the bandwidth and the services. So that's what's taking place here, is that the spectrum that was originally, a lot of spectrum was originally allocated to television broadcast, was sold off in a reverse auction. And the idea is that it winds up being more spectrum for the wireless users.
So more spectrum for wireless, especially down, what is this, in the 600 megahertz area, a lot of this spectrum?
Yeah, exactly. So what we're looking at is we're looking at basically what would occupy channels 38 through 51 now. So yeah, it's the 600 meg band. So the original repack was the 800 meg band, and then with our DTV transition 10 years ago, we had the 700 meg band, and now we're at the 600 meg band.
Now, to somebody who knows just a little bit about RF allocations, but not entirely, this kind of seems like a game of Tetris. We're rearranging existing TV stations so that they fit together better. They don't overlap. The protections are maintained, but there's maybe more efficiency to the plan once it's all done, and the existing TV stations are accommodated, but maybe packed in a bit closer, still maintaining separation. Is that kind of the idea?
Yeah, exactly. And that was one of the big benefits that happened when we converted to ATSC, to the digital television. Was under the old analog days, we had a lot of taboos. You had first, second, seventh, 14th adjacent channels that you had to watch. And now with the DTV, we're only looking at co-channel and then one channel either side that we have to do protections. And then even in the case when you look at the first adjacents, there's kind of a donut hole problem. So you can locate two first adjacents at the same site. And then as you get them further apart, there's a window in there where it becomes a problem, and then you get outside of that and you're okay again. So yeah, just by virtue of going digital, we're a lot more efficient with the spectrum anyway.
Those old separations required under the analog rules, was that due to intermediate frequencies inside the TV receivers, or what's the reason for all those exceptions?
Yeah, it was due to that, and then there were also images that would show up based on the oral carriers and the carriers and the interaction between them. So it kind of the analogy would be the guys that are FM guys. We all know about the 53, 54 channel separation. And so it was basically kind of an analogous version of that, just in the video world.
So what does this repack do on a practical matter for mobile phone coverage?
Well, with the mobile phone coverage, what we're going to find is that some of the carriers, and of course, I think we all know the big beneficiaries was T-Mobile, and of course, they were the guys that spent the largest amount of money, acquired the largest block of spectrum. It's going to significantly increase their capability to serve their customers and to make their customer base even more viable. I think one of the other things it's going to do too is you're going to wind up seeing some sort of redistribution in subscribers. So perhaps some subscribers that stayed on, maybe Brand V or AT&T, something like that, now that T-Mobile or some of the other guys have more spectrum available and can provide more reliable services, you may see some sort of redistribution in the carriers that people are using. So overall, I think what we may see is even the get a last spectrum, we're probably going to see some more efficiency in the way to operate as well.
Once the repack is done, is there more cell spectrum that has opened up? T-Mobile, I guess, in the reverse auction got a lot of this, but is there room for other carriers like AT&T and Verizon and any others to purchase more? Or is it all bought up now?
Well, I think for this go around, we're pretty well bought up because it was all done, in the auction. So, one of the things that they're right now is the C-band, and I think a lot of our our viewers out there, everybody should be aware of that. We did the C-band registration a year ago or 2 years ago, and now there's a lot more discussion in the reallocation of that as well.
Okay, all right. So in this whole process, were there any TV, I'm sure there's 1 or 2 or 10, was any significant number of TV stations that turned in their license or decided to go off the air and this is too much trouble or too expensive, and I'm not getting repaid fully or whatever? Are we losing any over-the-air TV channels from a practical point of view?
Well, from a practical point of view, no, but in terms, or not necessarily, I guess is what I should say, but in terms of how much spectrum is being used, the answer to that is yes. So let's take the Chicago market for instance,
Mhm.
and a lot of this the selling back of the spectrum occurred as a result of the duopolies that we find in some of the markets, which happened as a result of the change in the mobile owners. So take for instance, NBC of course owns Telemundo. And so in Chicago, they had WMAQ Channel 5 and WSNS Channel 44. They elected to sell the spectrum for Channel 44 back, and then they're entered into what's called a channel sharing arrangement. And I think everybody's probably familiar with the .2, .3 streams that we see nowadays. And by
Sure.
virtue of being able to carve this transport stream up is how we can allow multiple stations to use the same 6 megahertz block of spectrum. And of course, even though WSNS, as our example, no longer has their own block of spectrum, they are still considered a primary licensee by the commission. So they still have to do EAS, still have to comply with city license coverage. All the requirements that they had to do before, they're just sharing a 6 megahertz block of spectrum with another facility ID.
Ah, okay. All right. All right. So one of them is the main channel, one's a .2.
Yeah, exactly.
By the way, when stations do that, I typically see, of course, the main station will be in beautiful HD, pretty good bit rate, and then the others are carved up and they don't look so good. Would a station in Chicago do that, or would they balance the bit rate between the main and the second so they both look fairly good?
Well, it's a function, of what the programming is. So, right now under the ATSC 1.0 and new version, the 3.0, things are going to be a little bit different. But under the current scheme, you have a 19.39 megabit transport stream. And so you can carve that up as, however you sort of want to, but if it's like a pipe, the only amount of water flowing through a pipe. So the more you off, the less you have at the other end. So usually a lot of the guys will do an HD channel, and then you'll have several standard definition channels in there. And that's some of our, the smaller networks you see like the Antenna TV, the Get TV, things like that. And for them, running them in standard def, it's really not so much of a problem because a lot of that stuff is kind of, it's legacy programming or older programming and was shot in older formats. And so it's not done in HD, so you don't need the HD bandwidth to cover it well.
So we hear a lot in the news about ATSC 3.0 and how that's going to bring a lot of possible changes about should the industry, the TV industry, or individual stations or networks want to implement them. Does this repack we're in now, does it have any bearing on going to ATSC 3.0?
I think to a certain extent, yes, and because remember that the 3.0 is really a modulation scheme, and kind of what it is we as broadcasters have now got that convergence. I think people have been to NAB a lot of years. It was probably 15, maybe 20 years ago that NAB started talking about the convergence that was taking place in our industry, and now with 3.0 or next gen TV as it's being referred to now, we've gotten to that point where we really have the convergence between the IP world and the broadcast world. And by virtue of the high power and the large footprints that we as broadcasters have, there's a significant amount of efficiency that we have in getting programming material and that out there. It's still kind of looking at, how do we realize the revenue on it? So that is the thing that the business guys that are smarter than me are going to have to figure out moving forward is, how we do that and how we make money at it.
So let's move into a little bit of talk about what you do in terms of this repack. And I should say that when this repack, one more question, I guess, on that.
Sure.
TV stations oftentimes are having to change their frequency, but that doesn't mean that they're changing their advertised channel. Same thing that happened back in the DTV repack, right? Give us a little overview of how that works. I got to rescan my TV. The stations may actually be on a different frequency, but to me, it's still channel 5 or channel 11 or whatever it might have been on my TV, right?
Yeah, exactly. So is when you rescan your TV, it goes out and it finds all the RF channels that are out there, and it builds a table essentially that tells the TV receiver where to go look for a particular channel. So back to our Chicago example, taking NBC 5.1, prior to the repack, they were actually on physical channel 29. So that 5.1, when dialed that into your television, it went and looked for program stream 1 on channel 29. Now they're on channel 33, physical 33, but you're still going to see that 5-.1 in there. So that's the reason why the repack is so important, because what it does is it tells the TV set where to go looking for the individual streams.
So now, thinking about the work and the antennas that have been installed, of course, if a station changes their physical channel, their RF frequency, that almost always implies a new antenna, right?
Yeah, not only a new antenna, but in a lot of cases, perhaps even a new transmission line as well. So in some instances, yeah, exactly. So in some instances, what we had was stations on the last transition, they elected to put up a broadband antenna. Maybe they had one of these dual channel type of situations. Perhaps they were at a common site. Some of our vertical real estate guys have installed some large common antennas, and that was a practice that was pretty common in Europe. I think as Americans, we've always been kind of cowboys, and we want to have our own antenna in our own line. And here we are now 20 years later, and the whole idea of a community antenna, I think, is a lot more accepted than it was last time we did this. So if you've got one of those that was set up with a broadband type of technology, then you're just looking at probably a change in the transmitter and the filter. Other guys that had single channel antennas, like take a slot, they would have had to change their antennas, and in some rare cases would even have to change the transmission line. Everybody went through and itemized what they had, the commission looked at a lot of this when they established the channels, and the idea was to keep the number of transmission line changes as small as possible for obvious reasons. Cost money.
Oh, so you mean the transmission line change was actually a factor going into whatever computer algorithm was figuring out where stations would have to move? Wow.
Yeah, exactly. Yeah.
I've heard a little bit recently about elliptical antennas. What in FM we're so used to circular antennas, think that's the norm, and I forget, being a radio guy, the TV is typically what, horizontally polarized? Yeah.
Yeah, exactly. And as you and I talked last night, if you remember, if you look at the FCC rules, actually horizontal polarization is considered standard for both television and FM. In the FM world, we've gone to circular mainly, but it wasn't always, it was horizontal. And of course, the vertical only case is a special case that's allowed when we have the channel 6 protections in the non-com area. In the television side of things, the horizontal is also standard, but elliptical is being done nowadays because if you think about a mobile phone, the orientation of it, it's not a fixed antenna like you have with maybe rabbit ears on top of a television or something like that. So this phone is constantly moving around, and so by throwing some into the vertical, which gives us the elliptical polarization, what that does is it allows a greater signal to be captured by the phone. And circular is really a special case of elliptical, or you can look at elliptical as being a special case of circular. Circular is where the horizontal and the vertical components are equivalent. In elliptical, what you'll find is that one is not, is less than the other. So you get basically a shape of an oval, as it were, as opposed to
I have a question on the elliptical real quick. You said, so they're not equal on the elliptical polarization. Is there kind of a common ratio of horizontal versus vertical, Jeremy?
One of the common ratios that's been done a lot is, or that seems to be kind of one of the sweet spots, is 30%. So like at Willis, what we did is, and a couple of manufacturers have come up with some pretty cool ways of doing this, where they can actually change the vertical and the horizontal polarization at the combiners. And every station then, for instance, the New York project at World Trade, they have a variable polarization ratio allowed there. So each station can decide which amount of horizontal or which amount of vertical they want to inject back into the signal. In Chicago, well, so we didn't really have this physical space to do that. So what we did was we picked a particular channel and set things at a 30% ratio there, and then the other channels that are using the combiner just sort of fell where that fell. So we made it established, made the polarization ratio established at the antenna as opposed to being able to vary it at the combiner.
Oh, okay. Thanks.
Good question, Chris. We're talking to Jeremy Ruck. He's the principal engineer at Jeremy Ruck and Associates in Peoria, Illinois. And we've been talking about just some of the background of the TV repack and why that's all been necessary, and getting into a little bit of the hows and whys. But coming up in the next part of our meeting here, we're going to talk about some of the real specific engineering things. So Jeremy, of course, one of his primary tools is a vector network analyzer. That, along with a whole lot of experience in what he should be seeing with antennas and transmission lines. So we're going to be looking at some graphs and charts and seeing what some typical responses are from antennas and some pictures from the field. So that'll all be coming up in just a few minutes. Chris, why don't we pass it back to you, and we'll continue our meeting in just a few minutes.
Sure. We just want to take a little pause here and note that the SBE Webxtra is made possible by the generous support of our sponsor, Wheatstone. The SBE Webxtra will be right back.
Hello, I'm Jay Tyler with Wheatstone, and today we're going to discuss the advantages of going AOIP. If you're a broadcaster and you're either upgrading your facility, making a move, or just replacing a console, you probably are going to look at AOIP. And some of the major advantages of AOIP are the cost of savings on the installation. No more patch bays, no more expensive punch blocks, a lot less labor installing it. Secondly, sound cards. We can eliminate sound cards with AOIP drivers, saving sometimes hundreds of thousands of dollars on a single application. Next is going to be remote control. Whether you're a contract engineer or you want to have factory log in, we simply could not do that with traditional analog equipment. All of these AOIP systems allow factory remote control, engineer remote control, or even talent. So get in touch with their AOIP manufacturers today and find out how AOIP can benefit you.
And once again, we thank Wheatstone for sponsoring the SBE Webxtra. Did you know that by watching this webcast, you earned 1/2 of an SBE recertification point when you recertify? Just something to keep track of, as we talked about at the top of the show. So let's get back to SBE board member Kirk Harnack and Jeremy Ruck and all about RF and more.
Yeah, we've got some pretty cool RF here. I've, as a radio engineer primarily, I've dealt with AM and FM RF, and of course RPU RF and STL systems, things like that. Jeremy, you're dealing with high power and I guess typically UHF frequencies, some VHF, but you've got a lot of pictures and graphs to show us here off of your equipment. This is the truly educational part of the show where I'm looking forward to learning something. Why don't you tee this up for us, Jeremy? What would you like to tell us about what has to happen in the field to make sure this goes off correctly?
Well, one of the things that we want to make sure of when we get out in the field is that the antenna was installed properly. There's no damage in shipping, and that the tower crew did everything properly, and that there were no defects in the manufacturing. And most of the time, things work out very, very well. Sometimes, though, something gets damaged and we don't see it. And one thing to keep in mind is that the network analyzer is not necessarily a fail-safe way to do it, but because there are some things that get lost up in the antenna itself and they're hard to identify. But generally speaking, there are kind of a range of things that we want to look at, and by sweeping the antenna system ahead of time, we're going to be able to identify any problems. Similarly, as a system ages, you're going to see things that happen, degradation that takes place based on the construction of the system. And using the analyzer, we can actually identify those before they become perhaps a problem. And this is the importance of having baseline data. One of the things that I do is when we go out and measure these antenna systems on commissioning is I archive all the data that was done at the time that the antenna was commissioned. So whether I come in, 5 or 10 years later, somebody else comes in, I have that data saved, and we can give it to whomever, and they can overlay what they're seeing at that point with what we saw at the original installation and see what's changed and what's taken place over time.
So our producer Suncast is ready with the pictures that you provided. Would you like to start into those?
Yeah, so let's go ahead and let's look at number one here real quick. And what I want to show everybody here is that you'll hear guys that use a network analyzer talk about the frequency domain and the time domain. And we talk about the domain, we're looking at what's taking place across the x-axis of a particular trace. So what I've got here is I have 4 different traces, and this is actually the same antenna system. But what we've done is I've changed the span over which the transform is taking place into the time domain. And remember that it takes a finite amount of time to propagate through a transmission line. So that's how we can see what's taking place at different locations along the line. So in the upper left-hand corner, what we've got there is across the channel of operation. And what we're typically looking for there is that reflection at the very far right end is going to be the antenna. And I like to see that, 3% or less, which corresponds to about, 1.06. The one to the right of it, the upper right-hand corner, if you notice, we can see a little more resolution that's taking place here. And what I've done there is we've expanded out the span before transforming 3 megahertz either side of the channel. Down at the lower left hand, we've gone to a 100 meg span, and every one of those bumps out there is a flange in the rigid transmission line. As we broaden out the span, yeah, we can actually identify every one of the components there. And then the one on the bottom right covers the entire UHF band, and you can't really see it there. I'll show you one here in a minute. But not only can we identify the individual bullets and the flanges, but we can actually see the standoff insulators on the rigid sections of line. So we can identify, right down to a very fine resolution and an exact location where something is taking place. So let's go ahead and go to the next slide if we could.
Yeah, this tells me that via looking at these very tiny returns, these reflections, you can actually see parts of the transmission line that I thought were invisible, right? I mean, a piece of Teflon holding an inner conductor at the right place, I thought was invisible, but it's not, is it?
No, it's really not, because if you think about it, what's taking place is we're doing a very, very wide span here. And so it's just a little bit off or a little bit out. It's going to have a different impact depending on which frequency you're looking at. So what happens is over time, over the entire span, we're looking at an average. And so those very, very minute differences can then show up, and you can actually see what's taking place. And the time domain is really, really cool because it allows us to see what's going on that we might miss in the frequency domain. And I'll show you this here if we can go to number 2 here. So in this particular system, and this was a broadband antenna system. And what I did here was a 30 meg span, and I've identified basically, every 3 markers is one particular channel. Well, it's not really that bad. It's not ideal, but there's no such thing as a free lunch. So when we have a broadband type of system, we tend to have to sacrifice some of our return loss or VSWR in order to get the broadband. So this looks pretty, okay, fine. It doesn't look bad. Let's go to plot number 3.
Okay.
So what we did in plot number 3, if you look here, is this is our 470 to 806. So this is our time domain, once again, that we're looking at across the entire line run. Marker number 4 out in the middle here, this was, when I saw this, it was like, uh-oh, this is a problem. We need to find out what's taking place at this particular location. And if we go to the next one, if you would, number 4. What I did here was I span it out. And just a real quick note, if you look at number 4 is actually located at a flange. Number 3 is at a flange, and so is number 2. But if you look at between 2 and 3, there are 2 small blips out in the middle. That's our standoff insulators. So as you pull, if you pull a section of rigid apart and pull the inner out, there's usually going to be 2 insulators in there that keep the center conductor centered in the middle of the line. Number 4, though, is an impending problem. So let's go to 5. And it's kind of hard to see here, but if we go to number 6, you can really see what's taking place.
Ooh, ugly.
Yes, exactly. So what had happened on this particular line run, and they had really no indication that this was taking place. This is why sweeping your system every few years with an analyzer is so important. And actually, this system was shut down at the repack, and it's going to be re-energized. And we ended up changing, retrofitting the transmission line, fixing it. But this is an impending burnout that was just about to take place. And the reason I showed that frequency domain one back where we said, it doesn't really look that bad, is without looking at it in the time domain, we didn't really know that there was a problem there. We didn't know that something was brewing and that something was going to take place. And this guy was actually, very, very close to burning out. Can we go back to number 3 again real quick? Because I want to make one more point on that as well that we're looking at.
Slide number 3.
Yeah, that one right there. The other thing that's kind of interesting here too, if you notice markers 2 and 3 and 5, I kind of indicated them, and I indicated them because they kind of stick up and I only had a certain number of markers to deal with, but they kind of elevated above the rest of it. If you look at the rest of the line in there, we see kind of some irregularity in the flange reflections. So what that's telling me is that the bullets are aging, the watch band springs are aging in this particular run of line, and that this is ripe for probably getting a retrofit. And as it turns out, the line was, I think, 15 or 20 years old, so it was due to be looked at and to be changed out.
Now, but let's keep that graphic up for a sec. Just so I know, on the far left-hand side, points 6, 7, and 8. That's up close to the transmitter. Is that elbows, or what would that be?
Yeah, correct. That's in the elbow complex. So what we had is this particular run 8 was actually my test transition. This was a run of 7-inch, so that was the test transition connected to an elbow, which is why it's a little bit elevated. And this had a kind of a double rise in the elbow complex at the base of the tower. So that's what's taking place with 6 and 7. The same thing that you see way over at the right by number 1, which is kind of hidden just above number 1. We're getting into the elbow complex at the top of the tower as well.
Okay, and now all the really big points that are to the right of number 1, is that the antenna, or did you have the? Okay, that's the antenna. Okay,
yeah, that's the antenna. Good. Exactly.
All right.
And actually,
way,
if you look, sorry, go ahead. No, go ahead.
Well, I've noticed that earlier when you and I talked, and I've seen a presentation you give, you talk about S numbers or S points, and I've noticed that on these graphs, some of them, that one there, for example, just said S11. What is this nomenclature about S numbers?
Well, these are the S parameters. So if you think about kind of the easiest way to think about it is take a black box, and one side is port 1 and one side is port 2. And when we're thinking about an antenna system, we're looking at reflections. We're looking at the signal traveling to the antenna and then coming back, and we want to see what the ratio is between the reflected and the incident signal. So that's our S11 number that we're looking at. When we get into things like a combiner or a filter, we're looking at what does the filter do to the signal as it goes through it. And so that's when we start looking at things like S10, which is basically going from port 1 to port 2 on our black box. The S12 and the S22 are basically the reverse situations if you're looking from the output back in. But typically we're looking at S11 and S21 when we do broadcast type measurements.
When I think you told me about this some time back, when you say you take a baseline measurement and anybody else could use that data later on for direct comparison, is that because these S parameters and they're standardized in some way?
Well, exactly. So I use Dean Schwartz and the Copper Mountain families of analyzers, and both of those will allow you to export the data into an instrument state. And of course, the instrument state's proprietary to that particular analyzer, but you can also use what's called a touchstone file. And a touchstone basically gives you kind of a magnitude and a frequency. And everybody's analyzers and software, or even some computer software programs that will read the S parameters out of a touchstone file. So when you save that touchstone, and some of my colleagues, let's say, use the Agilent or the Keysight, they're able to import that data back in down the road into their answer. So it's kind of a universal type of format.
Moving on, did you want to pick back up with slide number 7?
Yeah, let's pick up with number 7. So the reason I threw number 7 in here is to show that you had talked about, looking at things that we're not sure really out in the line. This is actually what the signature of a run of semi-flexible coax, heliax, is going to look like. And we don't have those characteristic regular bumps because we don't have the flanges out there. So anytime you see something out in the middle, and I've got one I think later on here that shows some of that. A lot of times it's a case of the tower guys got overzealous with a grounding kit, or maybe there's actually a kink in the transmission line, and that will show up. This is a signature right here of what we'd expect to see with a particular run that was recently installed, and the tower crew actually did a good job with the install on it.
Yeah. Okay. What's next?
All right. So let's go to number 8. And the reason, if you notice this one, this is our 470 to 806 again, and this is a slice of a particular line here. And what I did was you see it's from 500 nanoseconds to 1 microsecond. This is essentially a 250-foot slice of line. But the reason I wanted to show you this is this particular line is made by a different manufacturer than the one I illustrated before. And because they use a different way of constructing their transmission line, it has a different signature that shows up on the analyzer. And so we can, you can look at the transmission line. If you do this enough times, you can look at it and say, oh, that's, Myatt line, or this is dielectric, or TRI, because they all have a distinct different signature to them based on the way they're constructed. So I thought this was something kind of interesting to share with everybody.
Cool. All right. What's next? Look at the next.
So let's go. Let's go to 9. So what I want to show on 9 is, and there are going to be actually 3 that we're going to walk through here. I think everybody's, or at least hopefully everybody's familiar with looking at the transmission line catalog. You'll note that only certain sections of line, certain section lengths, are valid for certain channels. I want to show everybody why this is taking place. So what I've done here in this particular plot is, this is a 100 meg span of a system, and you can see over here at the right we've got our antenna. Back down here towards the left, we've got the 2 larger humps at the left are internal to the building. And then we've got one kind of out there in the middle, just below marker 1. That's our base elbow. So what I did was I set up 2 markers between basically the top elbow complex and the base elbow complex. Let's go ahead and go to the next one. And what we're going to do here is we're going to apply what's called a gate to the system. And you can see once I turn the gate on, so what we've done is we've ignored everything outside of those 2 locations. Now we're still in the time domain here, so we're looking at each one of these bumps that's out there, remember, is a flange in the transmission line. Let's go ahead and go to the next slide. So then what we can do is we can throw this back into the frequency domain. And what you'll see here now is on the edges is just kind of the mathematical windowing that takes place. But what's very, very interesting to note is these 4 large reflections that show up out in the middle. Now, if you look right in the middle of the trace, you can see I got 3 markers there, and those markers delineate the particular channel on which the station was operating. The 4 large spikes that show up are what we call flange reflection pileup. And what happens is, when you'd mentioned, we talked just a little bit ago about these little tiny impedance discontinuities, well, we also get them at the bullets. And that's why we can see the bullets. So what happens is, though, over a long enough run, these guys add up, and they create a critical frequency where the VSWR, the VSWR, is significantly elevated at particular frequencies. And the locations, the frequencies at which these happen, are a function of the stick length. So let's go ahead and advance to the next one. And Kirk, you should remember this one from when I was out in Nebraska. This was a slide for my my network analyzer presentation. And this is what I want to show is, you can see that at 20-foot stick lengths, and that one we just showed, it actually worked out to 24.52. Every 24.52 megahertz with a 20-foot stick length, you're going to have one of these blips. And that works out to obviously about 4 channels. And you can see as we shorten the line sections, the span between the critical frequencies increases. There's the broad definition right there, and then 10-foot sticks have a critical frequency, notice that, of almost 50 megahertz. The reason I put the 10-foot in there is that, we look at some of the buildings like Willis and, World Trade, some of them, trying to get a 20-foot stick into the building is a little bit difficult. So in Chicago at Willis, we limit everything to 10-foot because that's what we can get around the elevators and the corners with ease. So that ends up spreading things out, and of course we've got a shorter run. And then the last thing is, you kind of want to stay away from 2 megahertz within a critical frequency. The old metric used to be like 3 meg. And if you look at the Wadelli catalog, they talk about 1.5 meg. So, somewhere in there, you want to give a little bit of a span. I remember doing, I did a checkout in Minnesota a number of years ago, and this was on a VHF station. And what they did was they actually had the wrong stick length for that particular channel, but it was installed under the analog days. And so that critical frequency occurred out between the visual and the oral carriers where there wasn't any energy. So when we're talking NTSC, it wasn't a problem. Once they went digital, it was a huge problem because of the waveform and the equal distribution throughout the channel. Now they got a real issue to deal with, and they ended up having to change the line out to get it to work.
I don't know if there's a quick answer for this, but to me, it's a bit counterintuitive that the shorter the stick length, the farther apart the critical frequencies are. Can you help me understand that?
Yeah, it's just the way it works out.
Oh, okay, all right. That seems
counterintuitive. Yeah, no, I know. It's just the way the addition is, the way things add up in the system.
What happens if you have a fairly short transmission line, maybe only 3 or 4 sections, but it's the wrong size for your critical frequency? Is that a problem, or is it only a problem when you get into longer lines?
Yeah, it's only when you get into longer runs. So when you start looking at a 500-foot run, 1,000-foot run, things like that, that's where it starts becoming an issue. 2,000-foot runs, obviously. When we've got these shorter runs, it's not really that big a deal because it just doesn't have enough for it to add up.
Let's you want to hit number 13? I think we're up to 13.
Yeah, let's go number 13. So number 13 and number 14 are going to kind of go together here, and this was another run that we did, and did this one I think last winter. But this has, and if everybody was paying attention, you should see that we've got a couple of different signatures taking place here. We've got that one that was a little bit different down near the front, and that first section was made of my transmission line, and then we've got a couple of large reflections. Then we get to an elbow complex, and then if you notice the vertical signature when we get out in there, let's go ahead and go to 14 if we could, and I'll show it a little bit better. You can see there is we've got a little different signature taking place in the vertical run, and in this particular case, it's actually old RCA line. But what was of most what was of most interest here though is this really large guy that we've got here at marker number 6 that's basically off the chart. And let's go ahead and go to 15. I'll show you what we found. Well, actually, back up one real quick. Sorry, before we do that. This 2, 3, and 4 out there, that's our tower base elbow complex. So between that and the large reflection, that's our horizontal run. And then we get to the vertical. All right, so let's go to 15.
It's that great big one there. Yeah, it's that great big one. Number 6. That's all right.
Yeah, sorry. So we can see here we've got some. Now let's go to the next one because then we can zoom in and see what's really taking place. So what was actually taking place is right here. What we've got is this unflanged transmission line, and you can see that the collar's not quite in the right spot, and actually the line was just a little bit short. It wasn't cut quite real well, and then we've got a transformer there and all that. So this whole combination right here is what gave us that pretty large signature. And as it turns out, in the channel of operation, this was also causing an elevation in the VSWR. But VHF high, so the station's running pretty low, not an issue for burning out in this particular case, especially since we're looking at 6-inch line. But the recommendation here was, hey, let's kind of rework this and make this look a little bit better.
You making me think of the old transition device. I'm sorry, I never was clear. Is it a whiskey cup or a whiskey cap that helps you transition between two different whiskey cup? Can you see those?
Yeah, actually you can. Now, if the whiskey cups were in the old 51.5 ohm line that RCA made, and of course,
be a problem. Yeah.
The reason why they made the 51.5 ohm line, don't you?
I'm guessing hardware store water pipe, but you tell me.
Exactly.
That's
exactly what it was. Yeah, exactly. Okay. Because it was a standard you could get at a hardware store. So if you had a burnout, run down, get some copper pipe, trim it, put it in, boom, you're on the air.
But you need a whiskey cup to make the transition. Right. Yeah.
Exactly.
All right.
So let's go number 7. Yeah, so let's go to number 17 here. So number 17 was an interesting one that we found, and the blue is a memory trace, and the red was the current trace. And what was taking place here was we had thermal changes when the station would go on the air and when it would go off the air. And so the blue was when we first got the test transition on right after the station went off. And then over time, you can see that the VSWR dropped. So on the top trace, I'm looking at basically just across the channel frequency domain. And in the bottom one, what we did here is this is in the time domain, and this is in return loss instead of VSWR. But the reason was to look at the differential in what was taking place with the reflected power. And if you notice, we had like a 7 dB change over about a half an hour in the reflection. So let's go ahead and go to the next plot. So you can see here, once again, red is now and blue is before. And this is another one of those maybe kind of counterintuitive type of things. But you can see that as it cooled off, it actually got worse. But the way the reflections added up, when the transmitter was operational, they would notice a steady ramp up in the VSWR over time as the transmission line heated up. Let's go to our next one then. There was our culprit.
Ooh.
Right there.
Oh, wow. And that's an expansion section of inner?
Yeah, correct. So that was a Bell's expansion section, and it just mechanically, I think over time, it just happened to go bad. And so that's what was taking place there is that is that this guy was about to fail. Now, once again, this is another one of those like the watchman spring that we showed earlier on. It was still running, but at some point it would have burned through. And this is kind of a cautionary tale too, to remind everybody that if you think you got an issue and you bring somebody in and they take a look at it and identify it, before you start taking stuff apart, make sure you got some parts on hand that you can put things back together. Because a lot of times, like in this particular instance, or the one that I showed earlier, if they had pulled the line apart and things had been active and they didn't have pieces to put it back together, you'd be off the air until they come in. So one of the ways to get around that is go ahead and go to number 20 is, and this is what we did here, is make a splice. So in that particular case, we were short. We didn't have another bellows section. So what we did basically was take another piece of line and figure out our differential that we needed, cut it down, make a little splice to put in there, and away we go. Now, obviously, that bullet out in the middle there without the Teflon on it, that's going to show up in our time domain, our wideband time domain. But at least it's going to get you back on the air at some level of power, 50%, 60%, something reasonable.
I found it pretty interesting. You pointed out over a 30-minute time, a 7 dB difference in the the reflected power and
reflected power, yeah.
And even at its worst, it wasn't catastrophic. This wasn't anything that you'd go, oh my goodness, we got to fix this. It's just like, it's more of a, wow, the reflected power goes up a little bit over time. And so you may not think that you've got an impending problem, but that really should trigger something. Things shouldn't get better or even get worse over time, should they? That should be about the same.
They should be stable. Yeah, absolutely. So you might see with filters, if they're not thermally compensated, as they heat up, things are going to shift a little bit. But there should be sort of a steady state equilibrium that we hit, and that really shouldn't want too much from that. Sometimes people say, well, it's cold outside or whatever. Well, yeah, but you're heating the line because you're running signal through it. So it's going to reach a steady state temperature. So if something's bouncing around quite a bit, you need to investigate that and figure out, especially something like 7 dB. I mean, that's a difference in reflected power of between maybe 30 or 40 watts and 80 or 90 watts. That's a significant change.
It is. And compared to how much going forward in that case, what was the case here? What was the forward power? Any idea?
I think the forward power on this was, 12 or 13 kW, something like that.
Okay.
So and that was, we're looking at 6-inch line here. So 6-inch lines rated much higher, closer to 60 kW. So 12, 13 kW, no big deal. It's just kind of idling along, which is one of the reasons that it was still running. Now, if they'd had a much higher power level, probably would have been off the air and burned through.
To me, it's worth noting that okay, so you've got a line that's rated for 60 kW. You're putting 12, 13 kilowatts into it. Your reflected power changes from 30 or 40 watts reflected to 80 or 90 watts reflected. A lot of engineers wouldn't think that was a bit. They might go, there's a little something wrong, but man, my coax will easily handle this. But what you don't know is the thing that's causing that difference is a really weak link, and it's going to fail.
Exactly. And we always, a lot of times we look at, VisWar meters, reflected power meters, and they're good to tell you a change. You should really never rely on them as an absolute value, especially ones in the transmitter. But what you should do is look for any kind of a change that takes place, and any change that happens is something that should be thoroughly investigated. And of course, like we said earlier, if you're sweeping your line, every few years, you're going to have some pretty good data, and you're going to know if something's taking place and changing.
That seems like, gee, that's like getting a good physical from your doctor and having a baseline and being able to compare yourself a few years later. I think that's the end of our pictures. Was that it, Jeremy, for the pictures?
One more slide, just one more slide real quick. And this is just kind of what I tend to look for in terms of specifications when we look at something. And obviously this is kind of an older slide because I still got NTSC, but just to give you an idea that, for FM, 1.1, that's what I like to see. And a lot of guys, oh man, you're going way overboard having it that low. No, actually your oral performance, your audio performance will be much better if you can hit these kind of numbers. 105, 108, 1.1, and then our DTV numbers, and then there's our far end spec. And then that flange reflections, ideally 1008. That's our wideband time domain that we're looking at.
Screenshot this picture, ladies and gentlemen. This is a good one to screenshot. I would keep that handy. Good information. Jeremy, the one thing from the first part of our show, by the way, we're talking to Jeremy Ruck. He's the principal engineer at Jeremy Ruck and Associates. A lot of experience in all this TV repack and transition. Has been doing this kind of stuff for years. And I think he and I were on the Sears Tower together many years ago, looking out for RF exposure issues there. Jeremy, you mentioned that once we get through this repack, and we're what, about maybe 60-70% of the way through it now as it goes to different phases, right?
Right.
After that, you said you're still going to be busy, and so will tower crews, antenna crews, and transmitter manufacturers, because those people who didn't make a change for the repack, their transmitters and systems are getting older, and they may be due for replacement in the next 2, 3, 4 years or so. Yeah.
Yeah, exactly. And not only do we have the guys that aren't being repackaged. Remember, I think the count was, I don't know, 1,040 stations, something like that, that are being repacked. It's only well, it's a significant fraction. There's still quite a few stations that haven't been repacked. And so depending on when those stations did their transitions, they've got equipment that's, at least 10 years old. And in some cases, better than 20. So, there's going to be a move on for those guys to do their changes. And in fact, one group that I work with has already started a plan to do that. But then the other thing that's taken place too is because, let's face it, there are not a lot of antenna manufacturers. There are not a lot of transmitter manufacturers. And there aren't a lot of tower crews or engineers. We've got kind of this, quasi-mature marketplace here. And so to get through this repack and the short time that's been allotted to us, a lot of stations have had to go with an interim type of solution. So as you and I talked last night, Kirk, depending on who you speak with, you're going to get a different answer as to how is the repack progressing. I think if you talk with the commission, they're going to say, hey, everything's great, everything's fine. But they're looking at it mainly from the point of view of, everybody changing the channels and getting off of the channels so it can be reused for the wireless guys. If your metric is my contours and my coverage is back to what it was before this whole thing started, well, then we're, maybe 50%, maybe even less than that. So we've also got that entire sector of the industry, guys that are on interims right now that are going to have to do their final solution as well. So yeah, there's, we talk about this being a 39-month process. And remember last time it took us, 10 or 15 years. So, we're still going to be doing this for a while once the advertised time is all done.
Jeremy, I'm overwhelmed with information, and thank you for all those graphs. Chris Scherer is standing by. Chris, I've kind of got my questions answered. You got anything else that you're wondering about?
I'm just trying to keep up at this point. I've always claimed I'm the audio guy who got dangerously close to RF, so I'm sort of hanging on by my fingernails on some of this. But it's great information. This has been fabulous.
Jeremy, might like to leave our listeners and viewers with a tip or any final thought before we go. Do you have a thing that you wrap up your demonstrations and talks with?
Well, I think, it's like everything. One of the things that we as engineers need to do is be very observant of our surroundings and keep an eye on your system. If you see something changing and something taking place, investigate that. No matter how small it may be, it could be an indicator of something larger is takes. The AM guys, one of the things that always bugged me was when the commission got rid of the base current requirements, that, that was always kind of a third check on an array. Because your phase monitor goes out, don't turn it on the cranks. Walk through things methodically, and there's always a root cause, no matter how simple or silly it may be. You're going to find that cause if you look at it. And if you get stumped, call somebody else. There are a lot of talented guys out there that are more than willing to help you out and give you pointers and tips on doing things. We're all on the same team and all working to keep our industry going.
All right, Jeremy Ruck. It's the principal engineer at Jeremy Ruck and Associates. Jeremy, this has been so educational, and I really enjoy it when you speak at a seminar like at the Wisconsin Broadcasters or Nebraska Broadcasters, where I saw you last. Thanks for all your work that you do and sharing your knowledge with others. It's great that you're doing that. I really appreciate you being here.
Sure. Thanks, Kurt.
All right. You. And Chris Scherer, it's been a good technical show. I've enjoyed what I've learned. Back to you.
As have I. Again, thanks, Jeremy, very much for coming in and sharing your your wealth of knowledge with us. Sort of a little personal plug on my end. In a previous life, I was an editor of a trade publication, you may all remember, called Radio Magazine. And Jeremy had picked up the reins on our RF engineering column for a number of years. And I learned a lot from him, just reading and editing his columns for that as well. So we're very happy Jeremy was able to join us today. But thanks all for watching today's SBE Webxtra. This episode will be available on demand on the SBE YouTube channel. And by watching this webcast, you earned 1/2 of an SBE recertification point when you recertify. So again, we thank our sponsor Wheatstone for supporting the SBE Webxtra, and watch for the announcement of our next edition on the this chapter of the web next month. It's usually on the 3rd Monday. So on behalf of Kirk Harnack, I'm Chris Scherer, SBE Member Communications Director. Thanks for watching, and we'll see you next month.